again. Yeah, now it says rec.
I forgot to make a remark here that we don't actually need to know everything about this pi because only this ratio matters, so we don't need to know anything about, say, normalizing factors or something because they'll drop out anyway. But I had a little discussion with Richard in the break and that made me question something, so maybe we can talk about that. So we said, well, we could just take a uniform distribution because that satisfies these rules, but then this Q will always be 1. Oh.
Yeah.
And it seems like that would be a problem. I'm not sure if it is.
That won't be a problem.
Is that not? Okay.
I mean, anyway, the pi is completely subjective, so you can take Q always 1 and that won't be a problem.
Right, so in that case, wouldn't the algorithm work if we just remove the pi and we remove the Q and we say we always, if we're allowed to step, we do it? Wouldn't that be a simpler algorithm which...
Yeah, we may have
Well,
difficulty.
Sullivan gives this as example.
Sorry?
Sullivan gives this as example.
Okay.
For taking pi uniform. And
So
we
I
also
guess-
say,
I guess
if it's
we-
possible, then we move to the next one.
Right.
That's what it results.
Right. So I guess maybe we allow we make it a little bit more difficult in order for the convergence to speed up, maybe. I don't know.
Erik, just
Yes.
a note. I think you choose pi when you know that, for instance, in your fiber, some things are more likely to happen than others.
Right. So you want some control over that, maybe.
Yeah. That's the only reason I could think.
Yeah, that seems like a good reason.
Well, you wanted to converge to this standard hypergeometric logic, so you don't want it to depend on the pi very much, right? I mean, the final output isn't supposed to depend on the pi.
It's not. Yes, I agree. It's not supposed to. But maybe the convergence time does. I don't know. That's what I guess. Right. So as I said, we just reduced our problem to producing Markov bases, or maybe at least recognizing Markov bases. And the following theorem, which is the main theorem of the section in the book, and also the main theorem of the talk, will help us with that. But I will first need a bit of notation again. Here I should maybe give a warning that the book is riddled with typos, and some of them are here. For any v r, we write v plus to be the v plus the vector such that all its components satisfy this, and v minus so the reason why we're doing that is that we might be confronted with a vector that also has negative entries, and we want to split the positive and the negative entries such a way. So if we so now v plus and v minus both have non-negative entries, and we have v equals v plus minus v minus. Okay. I already did in the beginning, but maybe again I should recall the result that was treated in Means lecture. Which was that ideal. So this ideal is that, or we can just take it as a definition. The theorem, which I guess I'll call 4, a finite subset B in this kernel is a Markov basis if and only if the set plus, so we have a set of binomials where we let the range of B generate so so we know it is able to generate, we are able to generate it with some u and u primes, such that a of u equals a of u prime. And also maybe we should note that if V is in B and therefore in the kernel of A, then we get if V equals 0, and that equals A V plus minus A V minus. Not for all V, but for those V and B, because they live in the kernel. So these binomials do occur there, and we say B is a Markov basis if actually B is enough and we don't need the whole kernel.
So this is really in the polynomial ring and not the ring that David was talking about.
This is in the polynomial ring where we where we treat all the components of P as variables. Yes.
Sure, but
So-
David also inverted some of them.
Yeah, so I'm curious.
Oh no, we're not inverting anything.
I'm curious what would happen with that version.
Right.
So we really this.
And the theorem is if and only if, so it would certainly not be true for my idea if it's not the same, but it would give you something which might be close enough for a Markov basis to hold, so I don't know. It might be fun.
But there is, I forgot what the remark was, but there is a remark in the book that says you can do something similar if you're allowed to invert them, but I don't really remember what the remark is.
And do we need to know how we know whether some polynomials generate this idea? Because
Well, I guess you can. That's testable, isn't it?
so we do what?
That's testable, isn't it?
I can test whether it's in the ideal. I don't know if it generates it.
Hmm. Well, yeah. So they are in the ideal. That's the remark I just made. Right? Because of this property,
Sure.
we can take u and u prime equal to v plus and v minus.
Yeah, but now I want to know whether apparently I need to know whether they generate
Yeah.
the ideal. Now how do I figure that out?
I think you can do it if you go back to the combinatorics of these lattices, but then it's not at all clear why we bothered choosing IA in the first place, so that's not a very good I don't know. Hopefully there's a better answer.
I think the best way to do that is what David did last seminar
Yeah,
too.
but that was in a different ring. That's why I asked.
Oh.
That's a
David
good
did
question.
invert
I don't know. So I guess after this theorem we've reduced our problem again
Sure.
to knowing that, but I won't give an answer to
Ask Magma, right? If it's
Sure,
Indeed,
sure.
yeah, ask Magma. Right, so
Can you give matrix A to a computer algebra?
Right.
yeah, I guess that should be possible.
you can give the matrix A, and then so getting IA. So finding a finite Geometric set for IA, you can do. It's not very hard. I didn't write it down last week because I didn't want to, but it's possible. But kind of the way you do it is via Markov basis type stuff. So I'm a little bit worried that it's circular.
This may be circular. I want to say a bit about the proof, mainly because Sullivan basically doesn't. I mean, he does, and the proof I will give is based on his lecture notes, but I had to fill in some details, which I want to treat. So we assume that B is a Markov basis, and so because we know the proposition that Amin treated, it's enough to show that all of the elements of this form lie in the ideal generated by Gus. So we take U and U prime such that AU equals AU prime, is any of them, or maybe more properly I should say let these be given. And then if we assume that this is a Markov basis, we can take this V1 up to VL V, maybe plus or minus B, I think that was in there. Such that we have 1 U prime equals U plus the sum of all the VI. And note that these V's depend on U and U prime. You can't expect to do this, expect to use the same moves. Okay, so this is Erik. Yes?
So you're allowed to use some of these V's double, right?
Yeah.
Well, it's not.
It's not
Yeah,
that you-
it's circle L might be mine.
Yeah, there might be doubles in there.
It's not.
It's not what you wrote, but it's
Oh,
It
because
wouldn't be a set.
right. So maybe I should just write
Multi-set.
that's way, and then now we're allowed doubles. Yeah. Sure. And then Sullivan tells you, without telling you why, that we have the following equality. I want to sort of take it apart. So this holds. Now, why is it true? Well, let's look at some terms here. For the I equals 1 term, what do we get? We get BU. So V1 we don't get, so we get minus V1 minus times P V1 plus minus P V1 minus. And if we expand that, then we get P to the U minus V1 minus plus V1 plus minus P to the U minus V1 minus plus V to the 1. Yes. And now here these cancel, so we get P of U, and this is V1. So we get P to the power u plus v1, and here we get minus b to the u. And if you look closely at all the rest of the terms and you do the expansion, then you'll see that the p of u plus v1, that's exactly, for the next term, that's exactly again subtracted. So we get a telescopic sum, and the very last one, so for I equals L, we get p u plus sum v. So here we get p to the u plus the sum over all i's, because this VL plus and this VL minus together make up the VL, minus p to the u plus the sum up to L minus 1, and this term will this one will cancel with a term from the previous term, and this actually, by choice, this equals u prime. And then there's where we used 1. Where do we use 2? Well, we use 2 to make sure that all these things that we write down actually live in this polynomial ring. We don't have to invert any p's. Okay? And therefore, so because we've written this, we have now written every p. Well, I guess I switched the prime and the u prime and the u, but every pu prime minus pu is some polynomial times something that lives in that set that we had there. So so all of these guys of this form lie in the ideal generated by this, and by that proposition the whole ideal equals the other equals I of A.
Excuse me,
Yes.
exponent u plus v1 plus up to vi minus 1 minus vi minus is the created.
Sorry?
No,
Here, this one?
no, the first line is u plus v1 plus up to that exponent is created is non-negative.
Oh, that's a good question. I think. Oh yes. Well, is it?
Eric, in every component it's at least the same sum plus vi.
This?
Yeah.
Or this?
No, the exponent, this exponent is at least the same sum, but the last thing replaced with plus vi. And this is positive.
Why is it at least that? So the vi is also positive.
Because your vi minus, your minus vi minus is at least vi in every component.
So you're saying minus vi minus is at least
vi.
vi.
Should be right.
Yes, that is true. Yes, because this equals vi.
Or this.
No, this equals that. Right?
Well, minus vi minus is the vector of negative components of vi
Yes.
plus vi, and we know that when we put plus vi there, it's greater than or equal to 0, component minus.
Oh yes. So yes. So the reason
Yeah.
is that so v minus and v plus, they have zeros in disjoint places. They have a separated support. So therefore, yes, because so the v plus never interacts with the vi minus.
Yeah.
So that's true. Now for the other direction. So we now assume that this set generates I of A. So that means that every element, in particular every element of this form, can be written minus there. In such a way where these guys live in R. But so here we need to notice something, because if we write a relation such as that, all of these polynomials, we can just split it into terms, and we can look at the coefficients of every term. And because here we only have integer coefficients, all the terms that have non-integer coefficient, in the end they're all going to cancel. So we might as well not write them down. We can make it write an easier
You
expression.
mean the non-integer parts,
The non-integer parts. What did I say?
with the coefficients that aren't integers? I mean, you could still have 1.5.
Oh, true, sure. The non-integer parts have to cancel. Yes. So rather than take rather than take them into with coefficients in R, we might as well have taken them with coefficients in Z. Julian is shaking his head. So here Sullivan says something that I think is a bit of a bluff, which is false. Because he says, so if you do if you write down a relation like this, then you can you might as well consider this over the prime field, in which in this case is Q, and then he says, and then you can clear denominators to make sure that you're working over Z. But I don't think you can just clear denominators in a way that you're used to, because you can't multiply by maybe the least common factor of all the least common multiple of all the denominators, because then you get a multiple in front here. We don't want that.
Yeah, so the non-integer, the fact that the non-integer parts cancel, I don't think is necessarily true. I think it is true that you can reduce to Z.
Why is that not true? Because there's no non-integer parts there.
Yeah, but 3 non-integer parts could add up to something integral, and it might cancel against.
Right. Okay. So they cancel modulo Z.
Yeah.
Yes. Is that enough? I guess
Probably.
that is enough. Yeah.
Something like that.
So here you have to do something. You have a nice argument. And so by splitting up these polynomials, so actually take them in Z. There. And by splitting up the polynomials into terms, and by allowing these v's to be doubled, you can write this as something of this form. Right. So we might need to use some doubles for that. Okay, and now we can rearrange. Because these we can have a preferred order such that we get m, say 1 times v1 plus equals u this, and we will again, so we'll make a telescopic sum again. So P2 Mi, P2 Vi minus plus and P. And I have to confess that I didn't actually look at that in a very detailed way. I kind of trust that you can do that. But why do we need to do this? Well, we do need to do that in order to get back these relations. Notice that the relation 2 depends on the ordering of the v's. So we need to put an ordering on them such that this holds. Okay. And then the proof should be done. But there are some details to fill in, which I also didn't bother checking very carefully.
Sorry, I have to go. When we're done, can you take that and hide it in your office?
Right. So, just to finish off, a quick corollary, Markov bases exist, because that's also part of what this theorem shows, because, well, you can just start off with, we're going to try and generate such a V by just taking a phi in the kernel, writing down this element and see what it generates. And so that generates an ideal, and then we may add another V2, say, take this element, see what the two elements together generate, get a new ideal, and so you get a increasing chain of ideals, and because this ring is Noetherian, that will at some point stabilize, and the only point where you can stabilize is when you've got the whole of IA, and then you've got a Markov basis. So they exist. And I think I will skip the last bit because it was a little bit offside. I'll keep it up, thank you.
Is there any questions? I don't believe these leaders are very good. So this will continue after the break, or after the holidays. I think we're starting with chapter 13, but also if people have more suggestions on topics they want to see, then please speak to either myself or one of the other organizers.
I have a suggestion, because in this chapter I added sections 1 and 2, and I think that is the most sort of general, or it seems to be the most important thing. But in section 3, they produce Markov bases for a slightly different setting, and there's I think there's quite a lot of nice simplicial geometry that shows up in there. So that might be interesting to see, but I don't know if it fits in the general sort of overall plan. But I thought it was reasonably interesting. I didn't study it in a very detailed way.
All right, great.
It looked interesting.